Hello, so is my slide visible? Okay. So today I will discuss one of the important topics, that is precipitation hardening. Okay. So this comes under solid state phase transformations. So I'll classify just to show what kind of solid state transformations we can have. So we can have diffusion based or diffusion less. Again, in diffusion we have short range and long range. So what comes under short range? We have allotropic transformations, but there is no composition change, only structure changes. Massive transformation, order disorder transformation, spinodal, then long range there are like eutectoid transformation, peritectoid, and precipitation hardening. And here comes martensitic transformation. Okay, so now we'll go to precipitation hardening. So the basic is we should have a phase diagram. Mostly the alloys that are used for this are aluminum copper alloys. In other alloys also we can get, but these are standard aircraft alloys. Mostly strengthened by this precipitation hardening. So in this we should have a phase diagram, that is, suppose we'll take the aluminum copper phase diagram. This is the theta phase, that is nothing but CuAl2 phase. Okay, so this is approximately 5.6 weight% copper, and this theta phase, this is the intermetallic phase, and the approximate composition is 55 weight% copper. Okay, so this is alpha phase, this is liquid plus alpha, liquid plus theta. So when we have a phase diagram like this, and we can go to this temperature, here in this temperature we have a single phase, and then we cool it down. Suppose we take 4% copper alloy. So initially it was in single phase. Now when it comes down this Solver's curve, it is in the two phase region, that is alpha plus theta region. So theta will start precipitating, and that depends on various factors. So we can get only when we have this two phase single phase solution going to a two phase solution, then only we get this precipitation hardening. Now if we draw this G versus T, this is for theta and this is for alpha. So this is alpha and this is theta that I am showing here. So the driving force, what is the driving force for the precipitation? This. Suppose at this temperature we are considering, so this will be our delta GV, the driving force for the phase transformation. So suppose we take a composition like this. I'll show it in a GX diagram. I hope you are familiar with this free energy composition curves. So what will be the alpha curve look like? It will go something like this. Because it is solid solution, so it will be broader, and we take the theta phase, that will be bit narrower because it is intermetallic phase. Or we can say for any phase, because here, okay, this is fine. So this is alpha and this is theta. So to know the composition, equilibrium composition, we have to take a common tangent. So suppose we take a composition like this. The alloy composition is this. We take it as C1. Okay. So we see here, for this alloy composition, this much reduction in free energy is available if we take these two phases, mixture of these two phases, because this represents the mixture, rule of mixture kind of situation. So this is the exact free energy of this composition, and this is the free energy of these two phase mixture. So it is below this, so this will be more stable. So we'll take it as C alpha of theta, that is composition of alpha in equilibrium with theta, and this is composition of theta in equilibrium with alpha. Okay, so this is the driving force for precipitation. And another important diagram you should have in mind is how strain energy changes with the size of precipitate. So this is our strain energy, and here it is aspect ratio. It changes like this. Here it is disc shape, and here when it is aspect ratio is 1, we have sphere, and here it is rod shaped. So disc shaped precipitates have minimum strain energy. Again, when a precipitate forms, there will be trade-off between strain energy and surface energy. When these two are minimum, that size of precipitate will be favored. Okay, so in this aluminum copper system, we get generally zippy zones, which are copper rich clusters, and the shape is plate like. So what are the barriers for precipitation? There are two factors. One is, as I told already, surface energy, and second is strain energy. Because new surface is forming and there will be atomic like lattice parameter difference, and also the bond energies will be different because of the difference of atoms. So that will cause the surface energy and strain energy. This is lattice parameter mismatch. Like suppose we have a spherical precipitate that is nucleating. The atomic planes will be like this initially, and the matrix phase, initially it will be coherent with the matrix planes, but as it starts growing, these planes will not stay connected. So that will lead to semi-coherent or incoherent interfaces. But initially, any precipitate forms that is coherent with the matrix, and that is spherical shaped. And again, after that starts growing, that becomes cuboid or different, like in superalloys, nickel based superalloys, we see cuboid type precipitates. They grow at the later stage, they become of different shapes depending on their surface energy and strain energy. So there is a parameter that is called misfit parameter. If this is greater than 15 to 20%, we get incoherent interface. And it is less than 5%, we get coherent interface. GP zones come under this category, coherent. And which interface should have lower surface energy? Coherent interfaces. Why? Because of the continuity. Of the atomic planes. So these have lowest surface energy. And what does strain energy depend upon? That depends upon the misfit strain. Okay, we call it delta, that I have written already. That is lattice parameter of matrix minus lattice parameter of PPT precipitate by lattice parameter of matrix. So if this comes under 15-20% greater than, then it will be incoherent. Less than 5%, this is coherent. Okay, so another important thing is Ostwald step rule. That is, when a supersaturated solid solution that is in the single phase, that is going to nucleate two other phases. Suppose this is alpha supersaturated solid solution, and this is our equilibrium alpha plus theta phase. So even we have this much of driving force for the phase transformation to occur, still we have this much activation barrier. So what happens, instead of going in one go, it starts to transform it like this. It goes in steps. Like first it will start, it will go, then there will be another. It goes like this. So initially it is alpha plus GP zones, then alpha plus theta double prime, alpha plus theta prime, then finally alpha plus theta. So by this what happens, the activation barrier is decreased here step by step. So this is called Ostwald step rule. Remember this sequence, most of the time they ask this question. So now I'll draw a free energy composition diagram of the same alloy. Okay, so alpha and GP zones, they have the same FCC crystal structure. So when crystal structure is same, in the GX curve, the free energy curve is connected. Suppose this is for alpha and this will be for GP zones. And what about the other phases? This is for theta double prime and this for theta prime, and the lowest one is theta. So why is this? Because when the size decreases, because GP zones is the smallest of the around 30-40 nanometer size. So when a particle becomes very small, its free energy increases high due to increased surface area. There is something we call Gibbs-Thomson effect. So that depicts that when a particle size is small, its free energy should be higher. So GP zones have highest free energy, then theta double prime, then theta prime, and then final equilibrium, that is theta. So if we take common tangents here, This will be highest. It's hard to draw here. Okay, so this will be the highest. It should ideally go like a common tangent, but it is hard to draw here, so I'll just show this point and this point, they will be in common tangent. Okay, so one point is this, that is equilibrium with theta. This point is for theta prime. This point is for theta double prime, and this is for GP zone. So I'll write those compositions. Composition of alpha in equilibrium with theta, composition of alpha in equilibrium with theta prime, alpha with theta double prime, composition of alpha in equilibrium with GP zones. So we see the composition of matrix increases, goes to the higher side as the size of the precipitate decreases. This is weight percent copper. Oh no, this is okay, it's fine. It's small fraction or whatever you can take. This axis is for composition, this is for free energy. So accordingly, their Solver's curves will vary like this. So suppose this will be the curve, Solver's curve. What should be this? This is for, what is the lowest composition here? This one. That is theta Solver's curve. Another one, this one, this will be for theta dash. And then again, this one will be for theta double prime, and finally we get GP zones. So in the phase diagram, there will be 4 Solver's curves for each composition, for each of these equilibrium phases. Like for theta phase, we have one that has the lowest composition, theta prime has higher composition, then theta double prime has still higher composition, and GP zones are the highest composition. That is the composition of the matrix in equilibrium with all these phases, that is shown here. So if we take a specific temperature like this, okay, and if we suppose we homogenize it or solutionize it at this temperature, and we take it to this temperature and keep it here. So what will happen in this phase? Only, so for this what happen, only alpha plus theta will be remaining, because there is no driving force for these theta prime, theta double prime and GP zone to form, because this level of supersaturation, this dictates your which phase will form, that depends on this supersaturation. Suppose we take to this temperature, in this case both there is supersaturation for theta and theta dash. So in this case, if we take the temperature to here, both phases will precipitate. Similarly, you can say like to take like here we have all four phases. So where does the strengthening come from? So the main strengthening comes from the coherency strengths. So what are these? Suppose we have a particle. It has its atomic planes like this, and we have a matrix outside it. So if the particle starts growing, initially it will be coherent, but when it will start growing, these lattice planes initially they were in aligned with the matrix, but then they will start bending like this to maintain the coherence at the initial stage. So then what will happen? So these matrix regions, these are strained. There are stress and strain fields around the particle. So this will inhibit the motion of dislocations. So we know that anything that stops the motion of dislocation will strengthen the material. Strength increases with coherency strengths. Another mechanism is when we have particles that are incoherent. That means these matrix planes and these planes are totally not aligned at all. Then different mechanism work, that is we call Orwan looping. Suppose this is dislocation line and it is moving in this direction. When it comes here, so it will bend like this and then it will move further, creating a loop around this and also around this. So many dislocations, when they move, they will create more loops around this and more loops around this. So as we know, the stress required is Gb by L. So this L reduces between these particles, this distance is L. So as this keeps reducing, we need higher and higher stress for the dislocation to move. So this is called Orwan looping. Okay. Okay, so now we'll see this curve, the hardening curve or the aging curve. Here we have hardness versus time. So it looks something like this. Initially here GP zones are formed. They are totally coherent, so there is no strengthening. Then as class चल रहा है. GP zones, okay, initially they start forming, they are coherent, then they will start, as their size increases, the strength increases, hardness increases because of the coherency strengths, as I told. Then somewhere here theta double prime phase starts, theta prime, then finally theta. At this point it is a mixture of coherent, highest strengthening is obtained, when we have a mixture of theta double prime plus theta prime phase. Remember this. And the nature is semi-coherent, between coherent and incoherent. That is, some of the atomic planes are connected and some are dislocated, some are like displaced. So they cause these misfit dislocations, we call them. Like we have this interface here. One plane is connected like this, one plane is left vacant, then another plane. This is the precipitate, this is the matrix. Then one plane is not connected, another plane is connected. So these we call them misfit dislocations. And they cause strengthening. Okay, so hardness curves like this looks like this, and peak hardening is observed when it is a mixture of theta double prime plus theta prime. So how temperature will affect this? We'll see that here. So the hardness versus time. It will vary the temperature. We'll see how it should vary. So initially one curve like this. So here temperature is increasing in this direction. So what is happening with increasing temperature? The hardness is getting lowered, because the highest hardness is obtained while temperature is low. We increase the temperature, hardness decreases. Further we increase temperature, the hardness, this is for 1, 2, 3. T1 less than T2 less than T3. So why this is happening? First we know that as we increase the temperature, there will be faster kinetics. So this, what this will do. Okay, so first let me show another curve. Okay, we have this phase diagram. This is the temperature versus composition. And this is the Solbus curve. And we consider this composition. Okay. So at this temperature, this is the supersaturation. This is what drives the formation of precipitates. Okay, so at lower temperature, supersaturation is further increased. And further lower temperature, supersaturation is further increased. So from lever rule, we can say at high temperature, if we calculate the phase fraction of theta from this, at this temperature, it will be lowest because this is the smallest. At this temperature, it will be higher than this first one. And at this temperature, it will be highest because of the lever rule. We know how to calculate that. So first point is decrease supersaturation. At high temperature. Second is decrease volume fraction. Of precipitates because of lever rule. And also one thing, at high temperature, the size of precipitates will be higher. Why? Because of precipitate coarsening. or we call that Oswald ripening. So all these factors lead to decreased hardness at high temperature. Okay, so is it clear till now or any doubt? Okay. So now we have 15 minutes. I will just go through another concept, that is Oswald ripening. These concepts are really important. Like precipitation hardening is very important. Okay, so I'll discuss Oswald ripening. What is it? Okay, so again that same free energy composition diagram. So this time just for small particles and higher particles I'll show. Or I have shown already here. Here you can see for the smallest particle the composition is high. For this is the composition. For this is the composition. For this, and for this, for theta, this is the composition. So as the size of the precipitate is smaller, that is inside the matrix, the composition of the matrix at the border of the precipitate will be higher. So I'll draw it clearly here. This is for theta, I'll add S for small, and this one is for theta large. Okay. So if we draw a common tangent now, one will touch here, this one will touch here. Remember the nomenclature, how we'll do this. This is the composition of alpha in equilibrium with theta small. This is the composition of alpha in equilibrium of theta large. So we can see if we have a theta here, smaller one, and we have a bigger one theta here, both are theta, but one is small and one is big. So what will happen at this point and at this point, here the matrix composition, that is alpha composition, will be higher. As it is shown here, this composition corresponds to this higher composition of the matrix, and here this will be lower. So then what happens? We have two particles, one small, one large, and in between we have this matrix alpha. So if we draw the composition profile, So if we draw the composition profile, okay, suppose from this center, here in this side we have percentage of copper. This is around 55%. That is for GP zones. Okay. And here we have distance between particles. So as we have seen, this is our matrix, and here it is one particle, here it is another big particle, this is small particle. So the composition here will be higher. As I showed here, the composition here of the matrix will be higher as compared to the bigger particle. So here we have higher composition, and here at this border of this big theta and alpha, it is lower. So what will happen? There is a diffusional gradient set up between through the matrix from this particle to this particle. There is a diffusion gradient, so diffusion will start occurring. So if diffusion starts, what will happen? This part will dissolve, and here this part will start growing. Okay, so as this part is dissolved, this particles becomes further smaller, so its free energy will go further up, and this, as it is getting bigger, this free energy will go down. Okay, so again this gradient will be increasing. It will keep on increasing until this particle is completely dissolved. So the main point in Oswald ripening is bigger particles start growing at the expense of smaller particles. Until it dissolves completely. Okay, so this is the basic of Oswald ripening. You can go and read in Porter. It is given in much more detail. Porter and Sterling. All these things are given. For gate, I think this much is enough. So any doubt in this? Okay. अभी NPTEL में मेरा क्लास चल रहा है. क्लास हाँ. Okay, so there is someone at my door. Can you repeat higher composition, lower composition once again? Okay, sure. So, see, when you draw the free energy composition diagram, this is for small particle, this upper one, because we know as the particles become smaller, its free energy increases because of the surface energy increases. So smaller particles have higher free energy. So this is one small particle, this is one big particle. This has higher free energy and this has lower free energy. So when to know the equilibrium composition with the matrix, what we do, we draw a common tangent. Wherever the common tangent, that is the matrix G curve, the alpha G curve, that is the composition of the matrix in equilibrium with that particle. Okay, so for small particle, this is the equilibrium composition of the matrix phase, and for this large particle, this is the equilibrium composition of the matrix phase. So here we have alpha in between, like we have a matrix like this. We have two particles, one is small, one is big, and this is whole alpha matrix. This is our theta and this is our theta. Where did this come from? Okay. So if you see at this interface, the equilibrium composition of alpha, that will be this, and this composition, we know this is our composition axis or weight percent copper, you can say. So this composition has higher copper content, which is in equilibrium with the lower particle. So this composition, that is just adjacent to the matrix, this will be higher copper. And here for the bigger particle, you see this is the composition, equilibrium composition of the matrix. So just at the interface, the alpha that is there, that will have this lower copper content as compared to the smaller particle. So in between, this will be the same composition that we took, or we can say, suppose this is our initial composition we take for precipitation hardening, we call it C1. So everywhere it will be C1, but just adjacent to the smaller particle, this will be this, and this region, this will be, so 1 2, I'll write here, 1 is for small, 2 is for big. So this is 1, this is 2. Is it clear? Okay. So it's almost 8. So see you next week. Or next week, will there any class next week? Have they mentioned anything? Okay. Okay, so thank you. See you next week.